Today we're going to be tackling question 3 out of chapter 1.2, which reads, write out the Cayley table for the group of symmetries of an equilateral triangle, which is a group of order 6, the smallest non-abelian group. So try this for yourself, and then we'll do a couple hints, and then we'll move on with the proof. Great. For some hints, we note that we kind of already given that it's a group of order 6. And the biggest hint you can have is just remembering what a Cayley table is, which is the multiplication table for a group, namely written out in some sense. And then another hint is actually just try to get a physical triangle and try writing it out for yourself. Alrighty then. With that, we're just going to go on with the proof, which is not really a proof per se. It's just that there is a particular group needs to generate. It looks a bit like this. And let's kind of look through what this represents. If we have a triangle here, we label the vertices A, B, and C. We'll note that E is the identity element, such that if you multiply anything by E, you're going to get that thing itself, or E is just the idea of leaving the equilateral triangle alone. Let's look at the element R, which you can think of as a rotation. It doesn't really matter the rotation, but for our preferences, we'll think about it as a rotation to the left by 120 degrees. And we'll see that R times R, so doing the operation twice, is the same as R squared. So that means R squared is simply the rotation by 240 degrees. Or alternatively, you can think about it as a reverse rotation by 120 degrees. But let's not think about that for now. Next, we'll look at F, where F is the idea of flipping, in that you're reflecting over one of these lines of symmetry. And you'll actually see that each of these, F, FR2, and FR, are rotating against a different one of these, different lines of symmetry. And I'll leave it to you to figure out, based on the notations and the actual rotations, which lines of symmetry each one are. But F, think about it as a flip across one of the lines of symmetry, and figure out which one is which. Next, let's continue with the fact that this is a non-abelian group. And the way we show that this is non-abelian is we'll note that there are certain elements that if you do them in one order, it is not the same as doing it in the other order. So for instance, doing R squared, then F, is not the same as doing F, then R squared, since you'll see that these elements are not the same, namely that FR and FR squared are not the same elements. And you kind of check this in general. If it were symmetric, then choosing one and then choosing a row and then a column, or a column and then a row would be the same. But we'll see here that they are not the same. And there are certain things that if you do them in one order, is not the same as doing the other order. So we've confirmed that this is in fact a non-abelian group. And clearly this is of order 6. Namely, recall that a group of a certain order means that there are that many elements. That's the cardinality of the group in some sense. While an element can have an order, which is the minimal number, such that if you multiply it by itself that many times, you get back that identity element. For now, we'll note that we have our complete table, so we're going to call this question done. Thank you for watching.